Hi everyone, I'm Dan Fullerton, and today I'd like to talk to you about magnetic fields due to current carrying wires. So, our objectives are going to be to calculate the magnitude and direction of the magnetic field at a point in the vicinity of a long current carrying wire, use superposition to determine the magnetic field produced by two long current carrying wires, and calculate the force of attraction or repulsion between two long current carrying wires. So with that, let's talk about magnetic fields produced by wires. First off, moving charges create magnetic fields. We already know that. And current carrying wires carry moving charges. Therefore, they're going to create magnetic fields. And you can use the right-hand rule to find the direction of the magnetic field produced by current carrying wires. For multiple wires, you determine the magnetic field from each one, and then you add them up together using superposition. Now, also realize that magnetic fields interact with moving charges to create a force. So if there's a magnetic field, a current carrying wire can feel a force due to that magnetic field because it contains moving charges. So two current carrying wires can actually exert a force upon each other. Now, to determine the magnetic field due to a wire, as far as the direction goes, the first thing we're going to do is use our right-hand rule. Take your right hand and point the thumb of your right hand in the direction of current flow. If this is a wire, point the thumb of your right hand in the direction positive current is flowing in that wire, and as you wrap the fingers of your right hand around that wire, that shows you the direction of the magnetic field. That's the right-hand rule that tells you the direction of the magnetic field. So over here, if we have positive current flowing from the bottom of the page to the top, we will end up with this circular pattern for the magnetic field around that wire. The magnitude is given by mu naught, the permeability of free space, times the current in amps, divided by 2 pi times the distance from the wire, r, where mu naught is 4 pi times 10 to the minus 7 Tesla meters per amp. And if you have something other than free space or air, then you adjust that mu naught value for the permeability of that new material. So, if we have two current carrying wires that are parallel, we can use the right-hand rule to determine the force between them. For example, if we have two wires with current traveling in the same direction, well, let's find the magnetic field due to the first wire. If we look at the bottom wire as the wire we're going to focus on, using the right-hand rule, I can see that the magnetic field produced by this wire up above the wire is going to be toward me or out of the page, and below it, it's going to be into the page. Now I see that I have current flowing in this wire perpendicular to that magnetic field. If I use the right-hand rule, point the fingers of my right hand in the direction of current flow caused by this top wire, and then bend the fingers of my right hand in the direction of the magnetic field, I'm going to see that we're going to have a force on the top wire down. And if I reverse that, if I find the magnetic field due to the top wire and then find the force due to the moving charges in the bottom wire, I'd also see that we'll have a force that way, and they have to be equal by Newton's third law. So if the current is traveling in the same direction, the wires are going to attract each other. Similarly, a good exercise for you would be to pause this for a second and see if you can prove that these two are going to repel each other using your right-hand rules. As we're here, let's take a minute and talk about Gauss's law for magnetism. We've already talked about Gauss's law for electricity. When we think about it, you can never draw a closed surface with any net magnetic flux in it because there are no magnetic monopoles. You always have a north with a south, so anytime you draw a closed surface, the net is going to be zero. That's the basis for what we call Gauss's law for magnetism, which is Maxwell's second equation. The total magnetic flux, the net magnetic flux, is equal to the integral over the closed surface of the magnetic field dotted with the area, and that has to be equal to zero. And again, that's zero because the net has to be zero. There are no magnetic monopoles. No matter what you do, you get a north with a south. Let's take a look at a couple sample problems here. Two long current carrying wires are separated by a distance d, as shown here. What is the net magnetic field due to these wires at point P, located halfway between the two wires, if the top wire carries a current of 3 amps to the right and the bottom wire carries a current of 5 amps to the left? Well, let's start out by finding out what the magnetic field is at point P due to wire A. And let's call that one A and that one B. Well, its magnitude is going to be mu naught I over 2 pi r, where in this case our I is 3 amps, so that's mu naught times 3 over 2 pi, and the distance from the wire is going to be d over 2. So 2 times d over 2, that's just going to be d. I end up with 3 mu naught over 2d. And the direction by the right-hand rule, point the thumb of my right hand in the direction of the current flow, and as I wrap that around the wire, my fingers point in at point P, so that's going to be into the page. Now let's do the same thing for B. The magnetic field at point P due to wire B is also mu naught I over 2 pi r. Current now is 5 amps, so that's going to be 5 mu naught over, R is still d over 2, so that's just going to be pi d in the denominator. And by the right-hand rule again, as I check that out, the magnetic field is going to be into the page. So the total magnetic field then, at point P, due to those two wires, is going to be the magnetic field at P due to A, plus the magnetic field at P due to B, which is 3 mu naught over 2d plus 5 mu naught over pi d, pardon me, that should be pi d, or 8 mu naught over pi times d. And the direction, if they are both into the page, the total must be into the page. If they were in opposite directions, we'd have to subtract and take the net there. All right, let's take a look at one more sample problem here. Determine whether the two wires will feel an attractive magnetic force, a repulsive magnetic force, or no magnetic force due to the currents they carry. Well, let's see. They're going in opposite directions, so let's start now by looking at the top wire. As I look at this, current going to the right, down below the wire, I'm going to get a magnetic field that's into the page due to the top wire. Well, then I use my other right-hand rule down here. If I have positive current flowing to the left, and I bend the fingers of my right hand in the direction of the magnetic field, I'm going to see that I have a force down here that's down, that's repelling. And I could do the same thing to prove up here that I get a force that's repelling. And that makes sense because we know that current traveling in opposite directions in parallel wires is going to create a repellent force. So they're going to repel. Which wire will experience the stronger force? Well, that's just a trick question. Newton's third law says that they must be the same. Forces come in pairs. So they must have the same magnitude in opposite directions. All right, hopefully that gets you started with the fields due to current carrying wires as well as the forces between them, and also a very brief introduction to Gauss's law for magnetism. If you need more help or looking for more information, check out aplusphysics.com. Thanks everyone, and make it a terrific day.